MECH2410 Engineering Materials Tutorial 1 Atomic Structures and Bondings. This video will cover Chapter 1 to 2 of the textbook. And if you have learned DSC level Chem before, apart from atomic orbital, this tutorial will be easy and I think it is nearly a revision for you. Tutorial 1 Part 1 Atoms and Atomic Orbitals. An atom is the smallest constituent unit of ordinary matter that has the properties of a chemical element. Therefore, chemical properties of a material are closely related to the constituent atoms of that particular materials. This basically means that if you try to divide a piece of material into its smallest part, in which the small parts still has the same chemical property with the whole material, the smallest part or the smallest unit, which we will call it the atom. Atoms are constituted by three kinds of subatomic particles: protons, neutrons, and electrons. Protons, its symbol is here, have a positive electron charge. Electrons, the symbol is here, have a negative electric charge. Neutrons has a symbol of N, are without any net electric charges. And the amount of charge of an electron will be equal to that of a proton, but their signs are different. For protons, it is positive. For electrons, they are negative. But the amount, the magnitude of charges is the same. The nucleus, which is the central part of an atom, are constituted by protons and neutrons only. The mass of atoms are determined mainly by protons and neutrons. It is because mass of electrons is very, very small when we compare the mass of electrons to protons and neutrons. And the mass of protons compared to the mass of neutrons, they are nearly the same. Our particular concern will be how electrons in atoms are arranged, and this will be discussed in later slides. Niels Bohr has proposed an atomic model which calls the Bohr model, which have the following assumption. The radius of the electron orbits are quantized. Quantized means that the numerical value of such radius can only be an integer multiple of some fundamental constants. And that means the electron orbit, the values for electron orbits are discrete, and which is not a continuous. And also that means the orbital energy of electrons can also be the integer multiple values of some fundamental constants. And Bohr's model has some advantages. For example, it can explain why hydrogen's emission spectra are discrete. It is because, using this model, hydrogen's emission spectrum is produced by change of the orbits from one orbit to another orbit, from higher energy ones to lower energy ones, for example. And because the photon released is related to their orbital energy, their change in orbital energy of electrons, and because the orbital energy of electrons can only take several values, and that means the energy values for these photons can also only take several discrete values, and that explains why the hydrogen's emission electrons are discrete. However, there are some limitations in this model. First, Bohr model work poorly on atom other than hydrogen. And second, it cannot explain the bondings of atoms into molecules. And such limitation is mainly due to its half-classical properties. Classical here stands for classical mechanics in physics, and therefore such model is not correct in terms of describing the behavior of electron, and that's why later it is replaced by quantum mechanical model, which we use it today. Quantum mechanical model is the latest and the most advanced and accurate model we have for an atom, which incorporates the wave-particle duality of electrons. Such duality is mentioned in the quantum mechanics. Electrons exist like a standing waves around the nucleus, and otherwise, if we use classical mechanics, electrons will fall into nucleus and annihilate protons inside, and basically atoms cannot be formed. And due to using such wave properties of electrons, we cannot consider circular orbits, and there is no more circular orbits for electrons. And electrons now have electron clouds, which is a metaphor. But in other words, atomic orbitals, which is, you can consider it as a 3D shaped probability region or probability density in which you may find an electron, but not guarantee that you can find an electron there, which can be used, as I mentioned, to determine the probability of finding an electron in certain 3D regions in an atom. So basically, our 2D shaped orbits are changed to 3D shaped atomic orbitals, which describe the probability. And if you want a more accurate description, please take Chem 101, 1020, or Physics 3036 or 3037, and I will suggest you to take the Physics 3036 or 3037, which is the quantum mechanics. Atomic orbitals. Atomic orbitals are determined by three quantum numbers, n, l, m, and they must be integers. And each unique combinations of these three numbers constitutes an orbital. N stands for principal quantum number, and it must be larger or equal to 1, which indicates the electron shell number. The value for L must be in between 0 and n-1, which is the angular quantum number, which represents the subshell designation. For example, for L equals to 0, we call it S orbitals. For L equals to 1, we call it P orbitals, and so on. M must be between negative L and positive L, which is the magnetic quantum number, which represents the lobe of the orbitals. For example, the following examples described in the graphs are for P orbitals, in which L is equal to 1, so we have three possible values for M. M equals to negative 1, N equals to 0, and M equals to 1. And you can see that the orientations are different. And you can have an overview of the shape of all atomic orbitals: S, P, D, and F. For S, you may see that, and you may notice that the angular quantum number is 0, and that's why there is only one possible magnetic quantum number, which is 0. For P, the angular quantum number, which is L, is equal to 1, and that means M equals to have 3 possible values, and M is the magnetic quantum number. And D, therefore, will have 5 possible magnetic quantum number, and it basically means there is 5 possible shapes for d orbitals, and F, they have 7 possible shapes, and so on. And you need to remember that SPDF is determined by its angular quantum number, which is 0, 1, 2, 3, and so on. For each orbitals, we designate by the method I mentioned before. You can hold two electrons at the maximum, which is represented by sin number ME, which can be plus 1/2 or minus 1/2. And if you want to know why, you need to again take quantum mechanics. Electrons within the atoms fills the orbitals with the lowest energy level first, which is represented by or mentioned in of Bohr principle, and which we will use it in these courses. Different type of orbitals within the same shell, which means that different angular quantum number, which is L, the same values of N, will have the following energy levels, with S being lowest. S, which is L equals to 0, P which is L equal to 1, and so on. And within same types of orbital, that means same L, same angular quantum number, smaller n's will have a lower energy. That means 1s will have a lower energy than 2s. 1 stands for the value of n, and 2 also stands for value of n, and so on. And which is the order is mentioned here. And you may want to guess that in general, you have the following relation. But this is actually not correct. The actual energy levels for the questions or for the examples I mentioned before should have the following relation: 1s, 2s, 2p, 3s, 3p, not 3d but 4s, and then we come back to 3d, and so on. And which is quite different and not quite that straightforward. So how can we determine the actual electron arrangements within the atom? And we have following ways. The first thing, we can consult a graph, and this is actually some graphs of showing the energy levels, and you can see that 3D is actually higher than 4s. You can see that, and that's why we have the following orders for 4s and 3D. But there is some other ways to present this graph, and it is more straightforward, and which you can use it in this kind of questions. That if you write such kind of matrix, which is triangular matrix, and list out all possible atomic orbitals for n equal to 1, for n equal to 2, and so on. And you can actually observe that along the arrow directions, energy levels increases. And how can you know that? First, it is 1s. The first arrow you will draw it like this, which is start from the topmost one, and then 2s. Draw it from right to left, and then 2p, and then 3s, and then 3p, and then 4s, and then 3d, and so on. That's how you determined from the lowest energy electron orbitals, and that's how you find. And yes, we get the same results. And there's also another very useful relations: the maximum numbers of electrons within a shell. Within a shell means that the n, the principal quantum number, is the same for all electron orbitals within the same shell. It's given by 2n squared. N here also stands for the principal quantum number, and therefore it can also be also the number of shells where you count from the innermost one. Do you still remember the conditions for number m, which is the magnetic quantum number, and the conditions for L, which is the angular quantum number, which is listed here if you forgot? For s orbitals stands for L equal to 0, and the possible m is basically m equal to 0 based on the relation I specified here. And that's why the maximum number of electrons in s kind of orbitals is only 2, because there is only one type, one possible combination, which is L equal to 0 and m equal to 0. For p orbitals, L equals to 1, and there is 3 possible choice of m, and therefore there is 3 possible choice of 3 distinct kind of p orbitals. And that's why the number of electrons in p orbitals, the maximum number of electrons, is equal to 6. And if you consider the number of n necessary, the smallest p orbitals is 2p actually, because if n equals to 1, n minus 1 is equal to 0, and that means the L cannot be 1 for n equal to 1, and therefore for L equal to 1, or for it to be ordered, n must be larger or equal to 2, and that's why the smallest p orbital is 2b, and that's why in n equals to 1 there is only one s and there is no one p, and also there is no one d and one f, following the same logic I will actually going to mention. For d orbital, based on the same logic, you have 5 possible choices: L equals to 2, and m can be equal to -2, -1, 0, or 1 or 2. And the number of electrons, maximum number of electrons, is equal to 10. And d orbital, smallest one, will be 3d, based on the conditions for L. And for f orbitals, it is quite similar, and the maximum number of electrons is 14. And if you still can't understand the derivation, you just need to render the red part, which is the maximum number of electrons which each orbitals can hold, and the smallest orbitals for which can be appears for a certain number of n. For example, the smallest p orbitals is 2p, the smallest d orbitals is 3d, and smallest f orbital is 4f. And I of which g orbitals, it is very, very similar. G orbitals is just stand for L equal to 4, and it is very rare for an atom to have an electron in G orbitals. Example: please write down the electron configurations for an atom having 45 electrons. First, write the matrix, or in other words, the array first. How to write it? In this direction, it is in terms of ascending n. In this direction, it is in terms of ascending L. L, basically, for different values of L, the type is different. L is equal to 0, the type is S, and so on. And you still remember the maximum number. The 2, 6, 10 stands for the maximum electron numbers which can be contained in this particular electron orbitals. And basically we just write it out all done, and it will like a triangular shape. And then we just draw the arrows. The first thing is, remember that 45 electrons. So in each step, in each arrows, like I first put 2 electrons in the 1s orbitals based on the of Bohr principle, and based on the drawing arrows, which help me to determine which orbitals have the lowest energy. After electron is assigned to 1s, then 43 electron is left, and so on. Then it is 2s2, 41 only, 2p6, 41 minus 6, 3s2 minus 2, and 33, 3p6 and 4s2, 25 is left. And this arrow, fifth arrow, 7 is left. And then we come to the last arrow. Notice that there is only 7 electrons left. These orbitals can contain 10. Still, there is only 7 electrons that can be assigned to these orbitals. So, and then we just write down the final results. For other results here, we can just copy it from the array. And for 4d10, be careful that because there is only 7 electrons assigned to this orbital, so we write 47. And also be careful that it is for the number, the order for writing the result is following the shell number or the principal quantum number of these orbitals from 1 to 5, which is the ascending order. But yeah, this is the extra part. But the actual configuration is actually, be careful, 4d8 and 5s1 for the last few orbitals. And it is actually rhodium, if you have some knowledge in the periodicity table. And it is because half full orbitals, 4d8 and 5s1 are somehow more stable than 47 5s2. And in actual case, that means the array which use the Bohr principle is not always correct in actual cases. But if you basically such principle is already enough for these courses, as it is introductory courses and it is not a camp courses. If you want to know more, please ask your professors for more info.